Okay, welcome to EGR445 598 Mechanical Engineering Systems. In today's class, I'm going to continue the review of the concepts that we discussed in last class. And I would be happy to answer any questions you may have. That being said, let me once again ask if there are any questions from the material that we discussed in last class. If not, I will continue with the stress strain curve. Now, in last class, I briefly talked about the stress strain curve for the mild steel. So you have stress on y-axis, you have strain on x-axis, and if you were to apply this concept, this stress strain curve concepts in practical design, it is only applicable when the loading is quasi-static, which means the component is slowly stressed. If you were to stress a steel, a metal, ductile, or any type of metal very quickly, you are not going to get stress strain curve of this type. You are going to get something like this. And the reason for that is the material does not have time to react to the external loading if the loading is sudden. The most important part when we talk about the stress strain curve is the elastic region or the linear relationship between the stress and the strain. In the elastic region, stress is proportional to strain. So stress is proportional to strain. And the constant of proportionality is called as the Young's modulus. E is equal to stress divided by strain. It is called as Young's modulus. And please understand, Young's modulus does not differentiate between compressive and tensile stress or compressive and tensile strain, which means even if the component is compressed, so what it means is if you were to extend the stress strain curve in the negative direction, you are going to get the same Young's modulus. Now, here is the question which I always ask my students. You have talked about or you have studied, seen stress strain curve in tension. Have you seen stress strain curve in compression? In other words, when we plot stress strain curve, we have a metal piece that we pull on both sides. The material stretches. There is tensile stress, there is elongation, and finally we get this nice curve. But have you seen an experiment where something is compressed? No. Why? Because when you compress, the most significant failure that happens is buckling. Think about this experiment. You have a metallic bar and then it is compressed. Before the bar crushes, bar will buckle. And I'm sure you studied about buckling and Euler loads. So basically, what you have is you have this metallic rod and we apply load, and rather than failing in crushing or compression, this bar would actually buckle. And buckling is a very common failure for beam columns, which means the columns, the beams that are used to support the load vertically, the compressive load vertically, they are susceptible to failure in buckling. Now, Young's modulus deals with tensile stress by tensile strain or compressive stress by compressive strain. So Young's modulus is defined for normal stresses. Similarly, there is something called as the shear modulus, which is the shear stress divided by shear strain, which is also called as modulus of rigidity. And this actually also called as the shear modulus. Now, with this, remember, for an isotropic material, which means material where the properties are not direction dependent, you need only two parameters to characterize the material completely. What it means is if you can provide those two characteristics, all the material properties can be derived using those two parameters. So one is Young's modulus and the other one is Poisson's ratio. So you know this, but still I'm going to discuss what is Poisson's ratio. So consider a rod that is pulled on either side. So because of this pulling, because of the tensile loading, this rod is going to get stretched. The material does not, so the mass of the material does not change, which means once we pull this rod, volume has to change because the density is constant. What that means is after pulling, there will be change in the lateral dimension and there will be change in the longitudinal dimension. For an example, the longitudinal dimension L final will be greater than L initial. So L final will be greater than L initial, and D final, this would be D final, will be smaller than D initial. So this is what is going to happen. So what I'm going to do is I'm going to find out the lateral strain and I'm going to find out the longitudinal strain. The equation for strain is same. Final dimension minus initial dimension divided by initial dimension. So for lateral, this is going to be dF minus di divided by di. And for longitudinal dimension, which is LF minus LI divided by LI. So please observe, for tensile loading, the longitudinal strain is going to be positive, lateral strain is going to be negative. So we can define Poisson's ratio mu as minus epsilon lateral divided by epsilon longitudinal. So lateral strain is negative, longitudinal strain is positive. So this ratio is negative, but when we multiply that with a negative sign, we get Poisson's ratio, which is positive. So Poisson's ratio is an important concept that can be used for characterization of materials. Now, let me talk about stresses that we have studied in the past. First and foremost, what stresses come to your mind? So can someone point out or name few types of stresses? Shear stress we talked about. Normal stress we talked about. Principal stress, yeah. Von Mises. So I would start with a very simple case, which is bending stress. Okay. And we would use these equations in this class. So next concept is bending stress. So what is bending stress? So if you have a beam and if you apply a moment onto this beam, if you apply the moment onto this beam, what's going to happen is the top fibers are going to be compressed. So can you see that this fiber, initially the beam was something like this. The beam was something like this. Then we applied a moment. Because of the moment, the beam bent and then the top fibers were compressed and bottom fibers were stretched. So as you can see, there is compression here and there is tension here. So somewhere in between, as you go from top to bottom, there will be a plane where the fibers will not be stretched or compressed. So what it means is somewhere there will be something called as the neutral axis. And the neutral axis is the axis where the length of the fiber, if you were to measure the length of the fiber or length across the neutral axis, it would not change. It would be the same before bending and after bending. The fibers in this particular case above neutral axis are compressed and fibers below neutral axis are pulled. So they are actually, so what you have is you have tension at the bottom and you have compression at the top. That's why if you were to draw the bending stresses, you will see this type of triangular distribution where you have the maximum stresses either at the top or at the bottom. Everyone understood this? Can someone tell me the fundamental equation of bending? M divided by I is equal to sigma divided by Y is equal to E divided by R, where M is the bending moment. I is the moment of inertia. Sigma is the stress. Y is the distance from neutral axis. E is Young's modulus and R is the radius of curvature. So how do you find out the bending moment? Remember the shear stress and bending moment diagrams? Everyone comfortable with shear stress and bending moment diagram? Yes, no? Or maybe this is the time. Okay, so M is the bending moment, I is the moment of inertia, which is the second moment of area. Everyone comfortable in computing moment of inertias for the composite sections, rectangular cross sections, circular cross sections? Just for my own satisfaction, I'm gonna give you some expressions. So this is XX, and I'm gonna call this is YY. So IXX is moment of inertia about x-axis. If this dimension is D and this dimension is B, it is given as BD cube by 12. One thing to observe, that which dimension is cubed. So the dimension which is perpendicular to the axis, it is cubed. For example, IXX is the moment of inertia about x axis. So dimension D is parallel to x axis. Dimension D is perpendicular to x axis. So dimension D is cubed. Now, if I were to find out IYY, it's going to be DB cube by 12. Similarly, if you have a circular cross section of diameter D, the moment of inertia for circular cross section anywhere is pi d raised to 4 divided by 64. The moment of inertia is pi d raised to 4 divided by 64. Now, where do these bending stresses come in the picture and how do we use them? So let me take an example. Okay. So let me take an example. Let's start the simple problem. Problem first. Consider a rectangular cross section beam and this is the center line of the beam and there is load P. The length of this beam is 250 millimeters. Cross-sectional area, you can find out, say this is 50 millimeters and this dimension is 10 millimeters. So if load is equal to 2 kilonewton, if the load is 2 kilonewton, Young's modulus E is equal to 210 to the power 9 Newton per meter square. Young's modulus is equal to E 210 to the power 9 Newton per meter square. What I want to do is, I want to find out first stress, second deflection. So here is the problem, that you have a load P that is going through the center line of the cross section. This is called as axial load. So this is called as axial load. In axial load, the center line of the load passes through the center line of the cross section. Okay. Now, how do I find out the value of stress? How do I find out value of stress? Come on, tell me. So which is force divided by area. Now the load is perpendicular to cross section area. So this is the case of normal stress and the load is pulling. So this is tensile stress. So sigma T is equal to P divided by A. So what I want to do is, I will substitute 210 to the power 3 divided by 50 multiplied by 10. That gives me Newton per millimeter square. that would be the value of sigma t. Everyone agrees? Now the next question is, which is sort of important question, how do I find out the elongation of this rod? How do I find out the elongation or the deflection of this rod? The equation that is to be used is Young's modulus is equal to stress divided by strain. So let me rewrite this equation. What is stress? Stress is load divided by area. Do you agree with me? What is strain? Strain is change in the length divided by original length, which means this equation gets written as E is equal to P L A delta. So if I want to find out delta, which is going to be PL divided by AE. Now please note, dollars to dollars, pesos to pesos. This dimension is in millimeter. This dimension is in millimeter. But the Young's modulus is given in Newton per meter square. So I cannot have Newton per meter square on left hand side and Newton per millimeter square on the right hand side. They have to be consistent. So what I'm going to do is delta, I'm going to say 2 multiplied by 10 to the power 3. Length is 250 divided by 1000 divided by area. So area is 50 divided by 1000 multiplied by 10 divided by 1000, and then the Young's modulus, which is 210 to the power 9, and that will give me the deflection in millimeter, and it would be a teeny tiny value that you can calculate, but this is how you would find out the stress and the deformation. Everyone understood this? Everyone understood this? Yes, no? Now here comes the tricky question. What happens if that load P is not going through the center line? Same problem. And this is important because the levers and the beams, they are designed with this concept. Now, I'll try to sketch this, and then later we'll try to work out this problem. So now imagine same case. This is the central line, but load, actually we can make this super complicated, and I don't want to make that super complicated right now, but please try to understand. So this is the cross section, and the load, rather than going to the center line, it's somewhere here. What is the difference between the loading on the left hand side and the loading on the right hand side? So on the left hand side, you have axial load. On the right hand side, you have non-axial or eccentric load. So this is eccentric. Now what happens because of the eccentric loading? How do we solve problems like this? So whenever you have load that does not go through the center line, it gives rise to moment. So what it means, and I want you to understand this very carefully, this is very important, is if you think about it, and I'm going to show you, think about it like this load P is going to give you a moment and it's going to give you an axial force. So I'm going to solve this problem again. So next problem. So same thing. Now I will say find the stresses. Find the stresses. Wherein instead of load going to the center line, load is eccentric. And you can make this as complex as you want. You can have eccentricity along X, you can have eccentricity along Y, or you can have eccentricity along X and Y. So let me say this is, I'm going to call this as X. And I'm going to call this as Y. So what this means is right now, the load is offsetted by some amount. And I'm going to say, just for number point of view, so this distance is 50 millimeters. So this is 250. No, this was 50. No, so I shouldn't use this. Yeah, I'll say this is 25. This is 50. This is 250. And the load is same, 2 kilonewton. And there is, every force has equal and opposite reaction. Every action has equal and opposite reaction. So there is P over here. So if I were to look at this loading from here, so imagine that you are looking from here, you would observe something like this. Now what I want to do is, I want to use this information to find out the stresses. Now, the important point here is, remember, whenever you want to translate a load, you are going to get translated force and a moment. And I want you to understand this very important. This is an important aspect. So you have this load which is vertical. You have a center line which is on the left hand side of the load. So what I need to do is, I need to translate the load from right to left. And as I translate the load from right to left, I'm gonna get a moment. Which is going to be counterclockwise. So what it means is, so this can be represented as if the load is going to the center line and there is a moment like this. Now, what is the magnitude of the moment? The magnitude of the moment is nothing but the load multiplied by the perpendicular distance between the load and the translated position. So for an example, we are going to translate the load by 25 millimeters. So this moment is going to be M is equal to 2 kilonewton multiplied by 25 Newton millimeter. That is going to be the moment. The most important part here is understand that moment is counterclockwise. which means that moment is pushing the left hand side down and pulling the right hand side up. So recognize what that means is basically because of this moment, this side is gonna go up and this side is gonna go down. What is the implication of that? Implication of that is on the left hand side, you are gonna have compressive loads. On the right hand sides, you are gonna have tensile loads. You agree with me? So you have a direct load and you have a bending load. So basically you are going to have two stresses, and I'm going to say this is point A and this is point B. So check this out. So stress at A is equal to sigma D, sigma direct plus sigma bending. Now sigma direct is load divided by area, which is P divided by A. And sigma bending is M divided by I multiplied by Y. Equation for bending, sigma is equal to M divided by I multiplied by Y. Now it is important to note the signs. If you look at the direct load, the load is tensile, the component is pulled, which means if you assign tensile stresses to be positive, the direct load is positive, direct stress is positive. But if you look at the bending stress, since the bending stress is compressive, it has to have a negative sign. So I'm going to write this down here. P is 2 10 to the power 3 divided by area, which is 50 times 10 plus moment. Moment we know 2 multiplied by 10 to the power 3 multiplied by 25. Now the question is, what is the value of I? Now for finding out the value of I, remember the rule. This moment is about y axis. So I need to find out I, y, because the moment is about y. And when I find out the moment about y, it will be BD cubed by 12, which means 10. This dimension is 10. This dimension is 50 divided by 12. So this is going to be 10 times 50 cubed by 12. And y is the distance from the neutral axis. So the stresses will be maximum when you are the farthest from the neutral axis. And if you go farthest from the neutral axis, this distance is 25. So this is 25. But it is important to note that the bending stress is compressive. The direct stress is tensile. That's why it has a positive sign. And the bending stress is going to be negative because it's compression. So there is compression. So this is compressive. And this is tensile. Now what would happen at B? So at B, please note the magnitude of the bending stress is going to be the same because Y value is the same, M value is the same, I value is the same. The only difference is on B, the bending stress is tensile, Direct stress is tensile, so both of these stresses will get added. So at B, sigma B, you're going to have sigma direct plus sigma bending, and this will be tensile, and this will be tensile. Everyone understood this? Okay, let me take one more problem. And these problems are exactly similar to the problems from homework 1. So I would strongly recommend that today you can start working on homework 1 problem. So a punch is used to make 30 millimeter dia and 5 millimeter thickness blanks. The shear stress of blank material is 100 Newton per millimeter square. Find the punching force. So what is this problem? So in this problem, this is like a punch press. So this is a sheet metal. This sheet metal has the thickness 5 millimeter. Sheet metal has thickness 5 millimeter. And then there is a punch. It could be a mechanical punch, or it could be a mechanical press, or it could be a hydraulic press. And what happens is this punch actually goes down and then actually creates a blank. So something like this. And the size of this blank is 20 millimeter and 5 millimeter. Now, what he's asking us is what is the amount of punching force P that is needed so that we can create this blank. Everyone understood this problem? So what you have, think about it like you are creating a hole in the punch. So I mean, creating the hole in the paper using the punch. So just like that, you have a sheet metal, you have a circular punch that is going down, and you apply the force, and because of that forcing, there is a deformation, and that we get this small circular blank. How do we find out the amount of force that is needed to create this blank? Shear stress multiplied by area. Very good. But now my question to you is, what is the area?
The cylindrical like edge of where the punch, where the
Correct.
blank is being removed.
Correct.
where
So
the contact is no longer is.
so if you think about, let me draw you. So this failure, remember this word. This failure is called as circumferential shear. And we will study this in design of cotter joints. We'll study this in design of knuckle joints. So this failure is circumferential shear. And circumferential shear is, if you look at that, it is like if you were to stretch, if you cut that strip open and stretch the strip. So what you do is, so you cut the strip and stretch this. This is going to be pi times d. And this is going to be the thickness. So circumferential shear, so the shear stress, so P divided by A is equal to tau, because this is the shear stress. Tau is given as 100. P is something that we have to find out. Area is pi times d20 multiplied by 5. And when we multiply this, I can find out, so 100 times 100 pi Newton is the force that is needed to punch this circular plank. Everyone understood this? Now the next question is, and this is an extension of the same problem. We found out the
The problem you start,
oh yeah, then it would be 30. Sorry. This 30. Okay, so I think I got everything right. Now the next extension of this question is, what would be the stresses in the punch? Now I don't know if you have seen this happening. Imagine you use a material as a punch, and what you do is you use a hammer and try to create a blank or try to create a hole. But if that punch material is not strong enough, there is a possibility that that punch may crush rather than creating the hole in the blank. Basically, the punch would crush. So my question to you is, what is the stress in the punch? What type of stress would be generated in the punch itself? It would be compressive. Remember, so it's a normal stress, but it's compressive. It's not tensile, it's compressive. So that stress, so sigma punch is equal to P divided by A, which is 100 times 150 times pi divided by, what would be the area? Please note, if we want blank to be 30 millimeter, the punch has to be 30 millimeter. You cannot punch, you cannot use a punch of 40 millimeter to create a blank of 30 millimeter. So basically, you would have area, which is pi by 4, 30 square Newton per millimeter square. Everyone understood this problem? Similar problem is in your homework 1, so that should help. Now, this is a perfect time to cover a very important design of a component, which is called as design of levers. So design of levers. So where are these levers used? So if you think about an internal combustion engine, Okay, if you think about an internal combustion engine, there is a cylinder, then there is a crankshaft, and there is a camshaft. Camshaft and crankshaft, they are connected with a timing chain or timing belt. Remember, nobody wants to go through the dreadful breakage of timing belt, right? So you have a camshaft and you have a crankshaft. They are attached with a timing belt. So what you have is basically you have a lever, which is something like this. This is a simple lever. And what is the purpose of this lever? The purpose of this lever is basically the lever would give you a mechanical advantage. So for an example, if this length is L, this length is 2L, just think about it. If this length is 2L, what that means, if you have P here, basically the load here will be 2P. So basically the levers will give you mechanical advantage. Now the question is, what are the types of levers? You could have a simple lever. And by the way, a lever, simple lever, is a machine. If someone, most likely in EGR217, you might have studied the concepts of simple machines. So lever is a simple machine. And before we get into the design and nitty-gritties of the lever, I just want to specify what do we mean by a machine in terms of kinematic parameters. So this is a simple machine. So machine is used to change the power transmission characteristics. For an example, if you look at the force times the velocity on the left-hand side, that gives you the power that is changed by when you go on to the right-hand side. So the lever is going to give you mechanical advantage and it's going to change the power transmission characteristics. So for example, on the left-hand side, you have small length, but you have larger force. On the right-hand side, you have longer length, but smaller force. So basically, the characteristics have changed. Please understand, energy can neither be created nor be destroyed. Power is rate of change of energy. So power can neither be created nor be destroyed. So the power on the left-hand side is equal to power on the right-hand side, but the product, the terms in the product can be manipulated. And this is the same concept that is applicable and used in gears. So let's think about levers as simple machine that is used to change the power transmission characteristics. Now you could have a lever which is just horizontal, or you could have a lever which is something like a bell crank type of lever. And why is this lever called as the bell crank type of lever? I don't know. Have you seen those old church bells? So basically what you have is you have this bell, so something like this. And then basically someone pulls this or pushes this, and then you get that. Actually, I drew the bell on the wrong side. So bell should be here. So basically when someone pulls this, this lever hits the dong, and then basically you get that sounding booming noise. Okay, So this is called as the bell crank lever. In the bell crank lever, you have the same concept. So you have some load P, P1, you have load P2. This distance is L2. This distance is L1. And please note, what you have is you have a hinge at the center. So this is the hinge. Hinge cannot support a moment, which means the total moment at the hinge has to be 0. What that means is P2 L2 is equal to P1 L1. Everyone understood this? So how do you design a lever? Now, the design of lever is based on the principles of bending. So let me draw a lever here. This is the simple lever. And I'm going to show you something called as the rotated cross section. And this is a convention where the thickness is indicated in the same plane. This is the width or height, or I'm just gonna call this B, and you have B and you have T. And then on this lever, so you have this load P. And I'm gonna assume that this lever is attached on one side, and the length of the lever is L. Length of the lever is L. So this is a very classic bending equation. So first and foremost, here are the steps for lever design. Step 1, find out the bending moment. So find maximum bending moment. Second, assume B by T ratio. And usually B by T ratio is 4:1 or 3:1, which means B is 3 times the thickness, or B is 4 times the thickness. Then the third step is use the equation sigma is equal to M divided by I multiplied by Y, where sigma is the design bending stress. So this is a very simple process to design a lever. Have you done lever design as part of EGR444? No? Okay. So what is the difference between the mechanics of material and engineering design, or the mechanical engineering systems? In mechanics of material, EGR343, what they do is they give you the load, they give you the geometry, which means they give you the dimensions, they give you the locations, all the parameters are given to you, and you're asked to find the stresses. So we give you the dimensions, we give you the loads, and we ask for stresses. In the design problem, the material is given to you, which means the value of sigma is given to you. Either they would say the lever is made up with mild steel, and then you have to look at the design data book and find out what is the bending stress or what is the design stress of mild steel. They will actually give you the load, and they will ask you to design the lever. Design means finding out the dimensions B and dimensions T. So this is the design process that we are going to follow. Any questions from my in-class or my online students? So I will work out a design problem. Do you want a simple lever or do you want a bell crank lever? You can design any, actually bell crank lever would be nicer. So design a bell crank lever. Material is mild steel. The loads and dimensions are shown in figure. Find B and T. Find B and T on short side and long side or long arm. So what does this mean? So this is the bell crank lever. This looks like L. This bell crank lever has a long arm, and this long arm is say 250 millimeters, and this has a short arm which is 100 millimeters, and the load on the short arm is 500 Newton. And what we want to do is we want to find out the cross-sectional area of the short arm, and we have to find out the cross-sectional area or cross-section dimensions of the long arm. Now, it is important to note that the short arm and long arm could have same dimensions, but it's not required. You can have a short arm with different dimensions. You can have a long arm with different dimensions. It totally depends upon how the lever is designed. And in this particular case, I'm going to design this lever using different B to T ratios. So here is first thing is I need to find out what is the design stress for mild steel. Now, if you have the textbook that we are using for this class, if you go on to the appendix, they have given you the stresses for different materials. But the strength of steel, so usually the steel would go to the yield stress of about 300 to 350. Assuming factor of safety of 3 or 3.5, you can safely assume the bending stress for steel, mild steel, to be about 70 to 75 Newton per millimeter. And as we work out more and more problems, you would kind of get a feel for these numbers. Depending upon the material that you choose, the bending stresses or the design stresses would be different. For an example, depending upon the grade of steel you choose, the bending stresses, design stresses could vary significantly. But as a rule of thumb, the yield stress, which is the stress at point the steel starts losing its elasticity and move and basically you transition from elastic region to plastic region, is about 300 to 350 Newton per millimeter square. Assuming the factor of safety of 3 to 4, you get to the range of about 70 to 75 Newton per millimeter squares. So I'm going to assume, and this is the assumption, assuming sigma T bending is equal to 70 Newton per millimeter square. And that's what I said, that everyone's answer would be different depending upon the assumptions. So what I'm going to do is, first and foremost, I'm going to design the short arm. So design, so short arm side. So I'm going to assume B by T ratio of 4. This is assumption. So B is equal to 4 times T. Please note, this is assumption. Now I need to find out the bending moment. Now I'm going to assume this cross section. So where do I find out the bending moment? So I can find out the bending moment somewhere here. So bending moment max is 500 multiplied by 100 Newton millimeter. Sigma bending M divided by I multiplied by Y. So if this dimension is B, if this dimension is T, M is 500, 100 divided by I, which is, now in this case, this is going to be super important. Check this out. This is the section where it is bending. So if you look at this, this is going to be TB cube by 12. Multiplied by Y, which is B by 2. So please understand, this is the cross section. And this is the center line or the center axis of the cross section. So this would be I'm going to call this XX. IXX is equal to TB cube by 12. Now what I'm going to do here is I'm just going to use the relationship B is equal to 4 times T, or T is equal to B by 4. So this equation is going to be 500 times 100 divided by B by 4, B cube by 12, B by 2 is equal to, the stress is 70. So please understand, the only unknown that is on the right hand side is B. So you can use your calculators and find the value of B. Everyone understood this? Now, how would I proceed on to the long arm? So from here, you can find out the value of B, and T is equal to B divided by 4. So with that, you should be able to find out value of B, you should be able to find out value of T. Now, how do I go with the long arm? First and foremost, please understand, I do not know the bending moment on the long arm, but that is not required. Why it is not required? Because I can equate 500 multiplied by 100 is equal to P, which is here. So which is P multiplied by 250, and that should be able to give me the value of P. But at any rate, what do I need? I need the product of P multiplied by 250, which is same as 500 multiplied by 100. Which means I do not need to find out explicitly what is the value of P multiplied by P multiplied by 250. So on the long arm, so the design on the long arm, I can assume the same length. So I can assume or I can assume the same proportion, which is B by T is equal to 4, or I can assume B by T is equal to 3. And I can find out the moment. The moment is going to be P times 250 is equal to 500 times 100 and sigma is equal to M divided by I multiplied by Y. And please understand, here as well, the bending is going to be across this cross section. So I'm going to use the same equation. 70 M is 500 times 100 divided by I, which is T B cube by 12 multiplied by B by 2. So 500 times 100, and B by T is 3, so B divided by 3 multiplied by B cube by 12 multiplied by B by 2, and from here you should be able to find out the value of B, and then you should be able to find out the value of B by 3. Yes.
Why are we making the assumption B divided by 2 is 3?
Oh, because just we can. Because we are designing. So I mean, there is nothing wrong in if you say, hey, P by T is equal to 4. That's totally cool. But
Okay.
but in that's what I said in last class, that I should write this down. Assume. Why? Because I can. See. Okay. There is one more problem which I don't have time to solve, but I will set it up because this is in the homework. So you can have a lever, something like this. And here, same thing. You have this dimension as B, and you have this dimension as T. And there is a load P here. There is a load P here. This problem is different than the problem I just solved. what is the difference between the problem here and the problem that we solved on the bell crank lever? Please understand, on the bell crank lever, the load was perpendicular to the cross-section area. So basically it was going, if you look at the way that load was, it was direct, complete bending. Here, understand, this is the center line. So what it means is this load is offsetted by amount E. Now to solve this problem, what you'll have to do is sigma T or sigma bending is equal to P direct or P divided by A, P divided by A plus M divided by I multiplied by Y. So you are going to have sigma direct plus sigma bending. So sigma B, assuming it is 70, this is P divided by B multiplied by T plus M is going to be P times E. The I value is going to be T B cube by 12 and Y is going to be B by 2. I'll give you a minute to think about this. So what you have is on the lever on the right hand side, it is eccentrically loaded, which means the load is not passing to the center line. That means you are going to get the direct stress and you are going to get the bending stress. Now, I did not bother about signs, positive or negative, because in design, what we want is we want the maximum stress so that basically our design would be safe. That's why what I did, I added those together. So you have P B multiplied by T plus P multiplied by E divided by TB cube by 12 multiplied by B by 2. When you assume a relationship between B and T, so B divided by T is equal to say 4, this entire equation will get converted into just in terms of one variable that you can solve. Please try to attempt this problem, and if you want the solution of that problem, it's on the YouTube videos, so where I have actually solved 3-4 more similar types of problems. But this would be the perfect time to start your homework one.